Suppose we have a piece of cardboard that is 10 inches by 14 inches. We want to cut the corners of the cardboard to create a box as shown. Find the height of the box that will maximize its volume. In this problem, we're given information regarding the dimensions of the box, and with this information, we're able to think about how the base and width of the box affect its height. I can't stress enough how important it is to draw out a picture for these types of problems. Without any frame of reference, these problems can be extremely difficult to solve, especially when it comes to keeping track of the variables. We'll begin by looking at the volume of the box since it's the function we're trying to optimize. The volume of any box or cube is equal to its base times width times height. We know that one end of the flat cardboard is 10 inches long and the other end is 14 inches long. Additionally, since the piece of cardboard is going to be folded up to make a box, the corners that we cut are going to serve as the height of the box. To avoid having to deal with three variables, base, width, and height, we need to find a way to express the dimensions of the box in terms of height. Take a look at the diagram. Notice how the ends of the cardboard are cut on either side. Another way of thinking about this is that when we're finished cutting the sides of the box, we'll be left with the original length of the side minus the part we cut, which, as we can see, will be equal to the height. Knowing this, we can say our side lengths with the included cuts to our box will be 10 minus 2h and 14 minus 2h. Our volume equation is now expressed exclusively in terms of height. As with all optimization problems, we want to take the derivative of our optimizing equation. We set it equal to 0 to solve for any critical points, which will give us the maxima of our area function. Because we have a non-perfect square, we're going to use the quadratic formula to find the zeros of this function. Sometimes we get more than one critical value, but does that mean our function has two maximum values? No, it just means that the slope of our function changes from positive to negative and vice versa twice. We need to identify where the function changes from positive to negative to find the maximum value. We can do this by using the first derivative test. Uh, Surely enough, our value of 1.918 is in fact the critical point we're looking for. Another way to think about the two critical point dilemma is to look at what each value implies about the dimensions of our box. If we were to use that second critical point as our value of h, then we would get a box with a width of negative 2.164 inches, which isn't possible. After we've verified our critical value for h, we plug it back into the volume function, and we'll have solved for the maximum possible volume of the box. Once again, we're just going to plug in our calculated values for the sides back into the diagram to make sure there isn't any funny business going on. Beyond that, everything else checks out alright.